Today we will be presenting a Bathy DataBASE 3.2 webinar on optimizing your bathymetric data management. My name is Josh Mote, and I'm the Academic Liaison for CARIS. Here with me I have my colleague from down under, again, Daniel Crummell. So here you can see the CARIS ping to chart workflow. There's about 4 pillars. Each pillar has different aspects to it. The first aspect is for processing. For hips and sips and notebook, this is where you can bring in your data, process it, create a base surface, or with a notebook where you can bring in and create features that you can put into S57 formats. Then we have our analysis with the Bathy DataBASE suite, base editor, and the new engineering analysis module, which we're about to go over. We also have the production, which goes about for creating charts with S57 Composer and HPD, and lots, which is law of the sea, to calculate your maritime boundaries. And then at last we have discovery with Spatial Fusion Enterprise, which allows you to take all the data that you have and put it out on the web and put it out to those clients that you might have.
So getting back to the Bathy DataBASE product suite, it's definitely quite scalable to meet the requirements of each individual user. So to start with, we have Base Editor, which is a standalone desktop application. Base Editor is great for small to medium users who need some extra tools in bathymetric compilation and data management. It's great for bringing in data from various different sources like multibeam, single beam, LiDAR or historic data, and then combining, validating and visualizing the data. Base Editor is also really handy for bathymetric product creation such as soundings, depth contours and depth areas, all which can be used to help make ENCs and other products.
It's definitely right, Dan. Now, a lot of the people that have Base Editor might know that we actually have a step up from that, which is Base Manager plus Database Server. This has all the functionality of Base Editor plus the capability for data storage and management. Bathymetry models and metadata can be loaded into the database server and accessed using configured queries. Processes can be executed on the server, allowing users to utilize all the processing power of the server to combine surfaces and anything else that doesn't actually change an existing layer, such as extracting stuff and also creating contours and soundings. There are also admin tools to manage users and roles and database backups.
And in the 3.2 release of Bathy DataBASE, we've also introduced the separately licensed engineering analysis module that we'll be talking about more today. The module works with either the Base Editor or Base Manager application and provides extra functionality specifically targeted for ports and waterways users. This includes functions such as volume computations, reference model creation and editing, conformance analysis, and a set of tools for shoal management. We've had 2 big releases for Bathy DataBASE this year. The first of these was the release of 3.1 back in March.
One of the biggest highlights in the 3.1 release was the new Relational Database Management System storage option for Oracle Spatial 11G R2. This is in addition to the existing support for the PostgreSQL, which came out with 3.0 earlier last year.
We also made some other improvements, including improved security with account usernames and passwords being encrypted when sent across networks. We also introduced a best fit bounding polygon for all point clouds, which was a huge improvement over the minimum bounding rectangle that was previously used.
The export to surface to ASCII function has also improved with options to select the output coordinate system, and database operations were also improved with the new recycling bin and offline data layers for database collection layers.
And just a few months later, at the end of June, Bathy DataBASE 3.2 was released with even more improvements. Now, Bathy DataBASE contains an extensive level of metadata for its surfaces, and this functionality was enhanced with automatic capturing of metadata properties and the ability to export ISO-compliant metadata files.
We're now also able to store multimedia files, such as PDFs, TIFF, text files, and so forth, with any object within the database. A new warp function has also been added to transform data sets between horizontal coordinate systems, or to resample a base surface to a new resolution. Another handy feature in the new Compute Statistics tool, which allows users to compute the statistics for any layer in a point cloud or a base surface.
We've also completely revamped the profile tool. We can now dynamically display while digitizing profile lines, and multiple height sources can be displayed in the same window. In fact, there are so many improvements to 3.2, Josh, that we can't even fit them all on one page.
Certainly right, Dan. So on to the next page here. We can export high-density contours, depth areas, and other features into Bathymetric Marine Information Overlays, BMIOs. A BMIO product contains denser bathymetry, as in a meter up to a decimeter possibly, that what would normally you'd find in an ENC can be displayed as overlays in an ECDIS. This allows users to apply tides and water levels in real time to enable closer under-keel clearances. BMIO products are useful for applications where you need detailed and up-to-date bathymetric information. An example would be a large dredge project.
So, speaking of bathymetric products, our sounding creation tools have also been improved. We've implemented a quick sounding creator, giving users the ability to create soundings using the point-and-click method, and we also have an option to create soundings inside a contour. Once the soundings have been created, we've also given users the ability to display them in an engineering style rather than the conventional IHO format.
We also have given users more control over interpolating datasets with manual interpolation tools. You can now select exactly where you want to interpolate data using the point or click or the range method.
Well, Josh, we've certainly bombarded everyone with a heap of new features there, so how about a demonstration to show some of them?
Why not, Dan? So as you can see here, I already have 3.2 open. And as for display purposes, I have an ENC with the Port of Montreal already opened. Now that we have BDB open, I'm going to demo some of the enhancements we've already gone over so far. So to begin this demo, I'm going to use the import wizard to import some XYZ files. So I'm going to go up here to File, Import Wizard, and you'll see in step 1 we have the various different types of formats that we can bring in. So we have GSF, HOB, PFM, XYZ, and of course the CSAR point cloud. So I'm just going to go ahead and select Next, and then in step 2 we're going to select the files to import. So I'm going to select the XYZ data file and then select Open. Select Next. And here in step 3 we're actually going to select the input coordinate system, the horizontal coordinate system that was used when the data was collected. So being that this is in Canada, I'm going to select Canada and then go down to Quebec Zone 8 and select OK. Now for the Z-axis convention, this is very helpful if you're bringing in topographic data, which usually up is positive, or bathymetric data, where down is positive. So for here, we're just going to leave it as down is positive and the primary Z layer as depth. Then we have to select the info file. Info file is telling Bathy DataBASE how to read that XYZ data file. So select that and open, and then go to Next. Now in step 4, if we wanted to change right now what our output coordinate system would be for the horizontal, we could do that. But right now we're just going to leave it as the same. And then for the output data type, in the terms of our output options, we have point clouds and grid. The point cloud, seen here, is a CSAR point cloud which retains the true position for each XYZ data point from the XYZ file. We also have an option to create a CARIS grid directly and form what we call a base surface. Selecting the resolution, down here we can change this to any resolution we would want to, and then we have a griddy method that would go along with that. Now looking through here, certainly most common method used is the shoalest depth true position. Now this will find the shoalest depth in each node and assign that depth to the node, with the original location of the sounding being retained as an additional attribute. Now what we're going to create right now is just a point cloud. But for the second part of my demonstration, I'll be showing a gridded data set created with the 2-meter resolution and the shoalest depth true position. So I'm going to select the output file, and then Next. Now for step 5, I can limit what I import and give a limiting boundary rectangle, but for this demo I'm just going to leave it as the whole world. And then select Next. And then for step 6, This will allow us to map information out of the XYZ file and add additional attributes to the CARIS point cloud. But for this demo, I'm not going to do that, and I'm actually just going to cancel due to time. This takes about 40 seconds, but what I'm just going to do is open the file right now. So you can see the file has been opened down here. So I'm going to zoom to map, zoom down here, so we can see the point cloud that has been brought up. Now, with the parent layer selected over here, I can select the Properties tab and see some of the different attributes of what we actually are looking at. So you can see the extents, you can see the surface name, height, width, you can see the amount of soundings that were brought in is about 1.1 million. You can see the coordinate system, and so on. Now, with this shown, we can also look at kind of one of the new features that have been brought in that's kind of been added in 3.2, which is an updated bounding polygon. So if I select the bounding polygon here and refresh my screen, you'll see that now we have bounding polygon that better approximates the extents of my point cloud. Now, in previous versions, the point cloud would have had a minimal bounding rectangle, which is not very representative of the data. So now you can see that it's much more closer to the extents of this point cloud. And by selecting the bounding polygon, we can scroll down here and change the level of this bounding polygon to coarse, medium, or fine, with the default being medium. Now, I'm just going to go ahead and deselect this. And what we want to do is actually, because this is a point cloud, we kind of want to get to the level of base surface. So with sparse information such as point clouds, the user can actually create a tin that to create a base surface. And the tin, for those who don't know it, is a triangular irregular network. So what we're going to do is select the depth layer here and select Create Tin. So it's going to take a second. You can see down the bottom as the tin's being created. And once we refresh, we're going to see, mainly from this distance, we're going to see the long edges. But I'm going to zoom in so we're going to be able to see what the actual point cloud looks with the tin. There we go. Seem to be hung up on something there, but you can see we have all these long edges here. So what I'm going to do is zoom in to a much smaller area down here so we can see the point cloud in here with all of those long edges. There we go. So what we're going to do now is, once I created that tin layer, you'll see we have the depth tin and the tin editor, which are two additional layers. So with this long edges, what we want to do is get rid of them. So we're going to select the tin layer. And you'll see in previous versions before 3.2, we actually had a tin edge removal, which we still have, but with 3.2 we now have a generate coverage boundary. This command, as you can see here, is used to create a bounding polygon to limit the extents of the way that your tin by only encompassing legitimate data and excluding all of those long edges that we are just seeing. This command differs from the long edge removal because it provides a more custom result because of the boundary that can be edited. So here you can see the way that we're viewing the histogram as logarithmic or linear. You can see the shortest edge, the longest edge, and then you can exclude those long edges by a mean plus 2 standard deviation as user specified, or you don't have to exclude any edges. So here we're just going to use the standard deviation, and I'll select OK. And while that processes in the area, you can see now we have a bounding polygon that better fits what our data looks like with excluding all of those long edges there. So now I can go over to Tin Editor and actually update tin. And then it's going to generate a point cloud that looks much closer to what it should be. There we go. All right, so this is the first half of my demonstration, is going through this creation of a tin through a point cloud. But now let's get into the second part of the demonstration, and what I'm going to do is open that 2-meter base surface created using the shoal depth true position. So I'm going to go up here, File, Open, 2 meter. Now you'll notice over here in the left in the Layers tab that we have 2 different icons for the point cloud and for the actual surface. So this will help a user distinguish what they're looking at. So I'm going to zoom to map. Let's go ahead and turn off some of these others. Close that. There we go. So what we see here, I'll zoom in a little bit into this area. We were just looking at this area before. Here's that 2-meter grid. So with the parent layer selected over here, again we can see our properties of that. So we can look and we can see the resolution is 2 meters, the coordinate system, and if we go down we can see shoal bias true position is actually the gridding type that was used. So now to show you guys what I mean by that true position, if I select some of the grids nodes that are on here, what you'll see is a nice sparsely evenly spaced grid. Now if I select the depth, which again this is the true position of each sounding, and select, you'll see that they're not actually very nice and evenly spaced. They're kind of wherever the shoal was sounding that was attributing to that node actually is. So with these still selected, I'm going to show you how to display soundings. So with this selected, I'm going to scroll down, and with digits, I'm going to draw them. So we can see the hydrographic digits all over. Now what we want to see is engineering digits, which again is new to 3.2. So I can select that, and all of these digits now are engineering digits, which if we zoom in here, you can actually see the decimal of the engineering digit is actually where the sounding is located. And with this, I can change the precision to 2, and then refresh. And now we have 2 levels of precision there. So now, continue. I'm going to turn off these digits and zoom out a little bit. Now, if we zoom up to the upper part of the extent, we actually have some holes. And what I was talking about earlier was a new way that we can interpolate the data. So you can see that we have a couple of holes right here. Now, before when we interpolated data, we'd have to interpolate the whole surface. But with 3.2, now we can interpolate individual holes. So what I'm going to do is go to Tools, Surfaces, Interpolate. Let me select the parent layer. Now again, we can interpolate the entire data set, but right now I'm going to demo using by range and by pointing. So now we have a matrix size. The matrix size is stating around a single individual node. It's looking at a 5 by 5 matrix around that, and it's going to use 5 neighbors. If it has less than 5 neighbors around it, it's not going to interpolate it. So with that selected, we can select this hole and fill it in. Now again, we can use range as well. So we can select the range and select these other 2 holes. Now this can be really helpful if you want to interpolate holes within your data set where you might have some holidays and it's not as important to go back and resurvey the whole area, but you might have holes that maybe that was an island, or maybe you don't want to interpolate it. So this will allow the point and click for the user to go around the data set and kind of fill in all of those holes. Now we've done that, I want to go over the warp command. So what I'm going to do is right-click here on the parent layer and select Warp. Now with the Warp command, as stated, it can do 2 things. It can change the coordinate system. So what we're actually going to do here is change this to UTM WGS 84 18 north. And if we want to, we could change the resolution. Right now I'm just going to leave it as 2. The reprojection, we can make it fast or exact. And then for the interpolation method, I'm just going to leave it as bicubic. And the reason I'm going to leave it as bicubic is because it is the most robust, better results. It does create a little bit more memory, so it is a little bit more time consuming, but we're still going to go with that. And I'm going to select the output source as 2 meter. I'm going to select, just add bi in there so we know it's the bicubic. And save. And select OK. So here, didn't take any time at all. You can see that it actually is tilted a little bit because it's in that new projection. So I'm going to close the other surface there. There we go. So now on this new warped surface, I'm actually going to also go over the compute statistics. So if we see here, we're going to use our attribute layer. We are going to use depth instead of interpolated. And then for the bin size is actually, will determine the x-axis for the histogram that we're about to create. And for the histogram color, I'm going to change it to green, because green is my favorite color. So here in the compute statistics, you can see some of the statistics about the new warp surface. What is the minimum and maximum depth, the mean, the standard deviation, and the total count. You can see down here we can actually export this image to a PDF or to a TIFF file, and we can also export it to ASCII. Now, something else that we talked about was the sounding creation. So what I'm going to do is go ahead and open up a HOB file that I've already created. And this has soundings and contours in it. So with that opened, if I select the soundings and contours, it's kind of hard to see some of these soundings in here, so I'm going to select black. I'm going to change the size to 3, and then refresh, and there they are. We can see them a lot easier now. So if I scroll down, you can see some of these contours. And you can see some of those soundings as well. So what we were talking about is a new feature in 3.2 is the point and click. So what we want to do is say, for instance, this is a very shoal, maybe that's a rock right there, and I want to create a sounding on it. So what I can do is select Tools, Features, Create Soundings. Tools, Features, Create Soundings, and then Quick Create. Now here I'm going to make the designation layer as soundings and contours, and I can select either the shoalest value or the deepest value within my cursor area. So right now I'm going to leave it as shoalest, and I'm going to get all this information from the actual depth layer and select OK. And now you notice my cursor is a circle. So if I press Control and use the scroll of my mouse, I can enlarge the circle or bring the circle back in. So what we want to do is for this area right here, we want to find the shoalest area. So I'm going to just click, and it's going to create a sounding for me. So if we want to do something similar over here, I want to create it right here, I can do the same. So if we want to see in this large area, where is the shoal is sounding, you can make the circle quite large. You can see it's 9.4 right there. So this is pretty exciting. This allows the user to go through and again find those wrecks, find a rock or a shoal, and easily click and point and create soundings where they feel that it needs to be. So now that we've gone over that, what I'm going to do is show you the export to Bathymetric Marine Information Overlay. So what I'm going to do is select all for this, and then I'm going to do File, Export. So with these S57 objects, the HOB files selected, you can see that we can export to another HOB, S57, shape, ASCII file, DXF, GML, and KML. But right now we're going to go to a BMIO, and here you can see we can select the output location, the issue date, comments, being demo. We can make the individual cell code, 1, 2, 3. The producer we can make as CARIS, and you can see we have other attributes as we scroll down, being the height, the datum, and the owner, and so forth. So instead of creating this as well, I've already got one created for you guys. So I'm going to do cancel, actually open. So I'll do file, open. You can see we have this 000 file right here. Open that. Now what I'm going to do is turn off the sounding layers and this depth layer. You can see here, I'll turn this off as well. You can see here's our BMIO file. Now again, it's an S57 product, and an idea of a BMO can be displayed as an overlay in an ACTIS system, which will allow for people to send out notice to mariners and allow them to kind of look at layers when they need to. So before I end this demo here, I'm going to connect to a database. So I'm going to turn my depth layer back on. Turn this off. What we're going to do is connect to database. And here I've created a user as a loader. So I'll do loader and put in their password and log in. Now again, this is where the administrative controls for Bathy DataBASE server really come to play, so you can have specific users that can only access certain databases and only have the ability to do certain things, such as this example is to load data in rather than just to edit data. So then I'm going to select my Quebec database and then do connect. Okay, database is connected. Now what I can do is select the database here and do add surface. So I'm going to do add surface and add that surface to the database. And then you can see here we have some attributes of metadata that we can also add to the surface that we're adding to the database. So I scroll down, we can do the name of the platform, which would have been the vessel that this was collected with. We can see the survey technique. So for this one, it would have been, we'll just say it's multibeam, and do done. We can do survey start date, end date, survey type, status, and lots of other attributes as we go down. And then we'll select finish. So now you can see that we have an actual, let's see if I can turn this off. You can see now we have an outline of what surface has actually been added to the database. So I'm going to select the surface now and show you a really cool feature that we've added, which is adding attachments to certain things. So what we'll do is go up to Database and then select Attachments. So you can see right now, because I just put this into the database, nothing's attached to it. So I'll select Import, scroll down here, and we have some, we'll say we have observed tides, we have a photo, and a survey report. And then select Open. Now all of those files, being photos, text files, documents, PDFs, are now all attached to the surface. So if I close this and someone else goes into the database, opens the survey, they'll be able to do the same thing. Click the surface, go up to Database, Attachments, and they'll be able to open any of these files. Well, that kind of concludes my demonstration for today. So
we're just going to open up our PowerPoint back again. So as if all that wasn't enough, we've also engineered some all-new functionality with the Engineering Analysis module. Now, the Engineering Analysis module has taken a lot of functions from an existing CARIS application called BEAMS, which stood for the Bathymetry Engineering and Management System. BEAMS is a GIS-based application that was built to satisfy requirements for ports, waterways, and related market sectors. The application had 10 years of development in conjunction with users such as the Port of Hamburg, Port of Montreal, ports of Metro Vancouver, and the Army Corps of Engineers in the USA. A lot of the functionality has now been migrated to Bathy DataBASE as a module for either Base Editor or Base Manager to create an even more robust solution for our users. So included with the Engineering Analysis module is the CARIS Reference Model Editor, or RME. This allows ports and waterways users to create, build and maintain theoretical models of their channel or waterway. Now another really good feature is that the Reference Model Editor also has support for LandXML, which is a common exchange format for CAD applications. So this means that models that have been created in any other software and saved as a land XML file are able to be imported into Bathy DataBASE through RME.
Which is really going to be useful for a lot of our clients out there. Now, the most important thing that I think this brings to the table is volumes. Now we can computate volumes within Bathy DataBASE. So a number of different methods for creating volumes are available depending on the user's requirement. First, we have the rectangle volumes to provide a simple, quick calculation. For a more robust calculation, the hyperbolic method can be used. This creates a smoother surface for computations by using the center of each grid cell to construct a series of prisms. The triangle method can compute volumes from the 10 layer, meaning that the true position of the source depth can be used. Comparative volumes allow the users to compute the volumes between two tens, which could be used to determine the volume difference between a pre-post-dredge survey or to possibly look at sedimentation within an area.
Now, all of these volumes can be computed between the bathymetry data and a reference model, or the bathymetry data and an infinite horizontal plane for a more simple calculation. The results are stored as an XML file and can be exported to a text file or turned into a publication using the new publication tool in Bathy DataBASE. Conformance analysis allows us to display the bathymetry information relative to the reference model. It allows for a simple and quick visualization that can be easily customized. So in the example here, areas shown in red are danger areas where the bathymetry no longer conforms with the reference model, i.e. shoal areas. Yellow represents cautionary areas where the bathymetry is less than a metre below the reference model, and green represents safe areas where the bathymetry is over a metre deeper than the model. Now, these are just the default parameters, but they can be easily changed to suit a user's specific requirements, or you can change the units to feet for you guys in the US.
So, we have a comprehensive set of tools for shoal management. Users can automatically detect shoaling features within a channel or waterway and group them according to the depth or proximity in both a long track and a cross track. The shoals can then be stored in a reference in a database and have their status configured between active and cancelled. The publication function allows the user to easily generate a notice to mariners advising them of the shoal. So Dan, since I gave the last demo, do you mind giving the engineering analysis module demo?
Alright, so in my file, I'm a little bit more northeast than what Josh is, so I'm just up in the Channel of Quebec, which is a very nice part of the world that I was lucky enough to be in Easter this year when I was at CARIS HQ. So you can see that the data layers that I have open is I've got an ENC as my background, I've got a shoal survey, I've got my shoal survey post-dredge, and I've got my reference model as well. So you can see my reference model is divided up into a number of features. So I've got some alignments, I've got points that are the basic building block of my model, I've got a number of surfaces which represent my the theoretical model of my waterway, and then I've got some other data like some profile lines and some stations. So if we go and have a look at this, if I select one of my surfaces and have a look in the selection window here, you can see I've got the name for the surface, so surface 1. As I go through here, I've got my overdredge allowance, so my allowance below the surface, and I've got my maintained depth of 12 metres. So as we keep moving up, you can see I've got some chainages along the channel on my stations. So I've got another surface here, I've got surface 2. As we get up, I've got another surface here at the widening around the bend, and another surface at the top, which looks like the entrance to the channel. Now, the first thing that I'm going to show you guys today is that you can look at all of this in 3D, which is quite a handy feature. So if I open up the 3D viewer, I'm going to turn on my shoal survey, and I'm going to zoom into that. So here I've got my shoal survey, and what I want to do is I want to visually compare this with my reference model. So if I turn on my reference model, I'll turn on my surfaces, and I'll just turn on a few other layers. So I'll turn on profiles and stations. And what I'm going to do is I'm going to make my surfaces slightly transparent, so I'll give that a value of 25% transparency. And now you can see that I can view the bathymetry underneath the surface. And what this allows me to do is to easily visualize areas where the bathymetry no longer conforms, and I've got shoals. So you can see I've got one down here. Now this is the same 3D engine that we use in HIPS, so I can basically fly down my channel here. Can record this as a fly-through or provide it to people to look at in CARIS Easy View. And you can see as I get to the top here, I've got some more shoaling features. So you can see the sand waves that I've got on the left here. And also, if I want to be able to visualize this more clearly, I can use the vertical exaggeration to be able to really make my shoal features stand out above my reference model. Alright, so being that Josh is so excited about volumes, that's the first feature that I'm going to demo. So if I highlight my depth layer, you'll see I've got a couple of buttons up here. So I've got one for compute hyperbolic volumes and another for compute rectangular volumes. So what I'm going to do is go Tools, Volumes, Hyperbolic. And just to show that, this section here is pretty much the engineering analysis module. So I've also got, this is the reference model editor, so that's what will open CARIS RME in a separate application window. So going back to our hyperbolic volumes, you can see I've got my different surfaces for my reference model here. So I'm going to select surface 1 because the bathymetry doesn't have any coverage over any of the other surfaces. Or alternatively, I've got the infinite horizontal plane here. So we'll leave it at reference model surfaces, and we've got a number of algorithms for calculating our overdredge allowance, and I'm going to use wide bottom, which essentially calculates the entire volume of bathymetry between the overdredge allowance and the reference model in the calculation. So I'm going to pick an area to save that, and you can see that just to save a bit of time, because we are getting close to that hour mark, I've already created the hyperbolic and the rectangular volumes. So I'm just going to cancel out of that, and I'm going to open the volume results. So if I open results, I'm going to open the hyperbolic results, and you can see here that's the calculation that I've made. So you can see my reference template. You can see the overdredge algorithm that I've selected. You can see minimum and maximum values, an area to dredge, a volume to dredge, an overdredge volume, and a combined volume. Now this can be exported to a text file here, or alternatively, I can create a publication using the new publication. So I'm going to load up just a default volume publication that we've got. I'm going to select, this time we'll have a look at the rectangular volumes, and we'll create a publication out of that, and we're going to go preview. So here you can see just a basic little publication that we can print out or save as a PDF. And here we've got our surface. So here you can see we had surface 4 selected, but there's no data for it because there was no bathymetry overlapping that surface. And you can see that the rectangular results have given us slightly larger answers than what the hyperbolic volumes did. Now this publication can be customized to meet your own specific requirements, have your own logos in there. So the next thing I'm going to show you is tin volumes. So if I right click on Shoal Survey, and I'm going to create a tin similar to what Josh was doing before, and just to highlight that I'll turn off my other layers. So you can see there that I've created a tin from my grid. Now when I highlight the tin layer, you'll see that a button comes up here for compute triangular volumes. So I'm going to click that. And once again, the same GUI as before, so I'm just going to have surface 1. I'll leave wide bottom as my overdredge allowance, and I'm going to save volume results tin. So when I run that, I'm going to guess about 5 seconds. And you can see that was a very quick method of computing volumes, and it's given me very comparable results to what my hyperbolic method was. Oh, that only took 3 seconds. Certainly very fast. Alright, now the next thing that I'm going to show you is the new profile tool, which is really quite good. So I'll turn my depth layers back on, and I'm going to go Tools, Profile by Digitizing. Now this brings up the profile dialog, and in this I've got all of the available height sources that I've currently got open in BDB. So I'm going to turn on my reference model and leave that with a color of black, and I'm going to turn on the depth layer of my shoal survey. I'm going to give that a color of red. So you can see here that I can give a title to my graph or to my profile. I can give a label for the vertical axis, and we've also got the ability to change the sample step size. So I'm just going to leave those values there for now. I'm going to click OK, and you can see that the profile window is now displayed and my cursor has changed to a little digitizing cursor. So I can just click along, and as I digitize my profile, my display is dynamically updating in the profile window. I can hit backspace to remove points and add more, and that display will keep updating. So I'm going to end that line, and what that does is that saves that profile line in my newly created profile layer. So the other way that I can create a profile is I'm going to select one of the profile lines out of my reference model. So I'm going to select this profile line, and I'm going to go Tools, Profile, Super Selection. So it brings up the same GUI. So once again, I'll turn on my reference model and my shoal survey depth layer as red, and I'm going to turn on my shoal survey post-dredge layer this time as well as blue. This time I'm going to give it a title of Survey Comparison, and we'll just leave those values for now and we'll hit OK. So you can see this time, just to expand it out, I'll bring the window out. It's given me the profile for that selected line. So you can see my reference model here in black, you can see my shoal survey in red, and my post-dredge survey in blue, showing that the shoal has been removed. Now, any given time, you can right-click on this window and access the profile settings. So, for example, if I wanted to smooth that graph out, I can give it a sample step of 5 meters. And for my smoothing option here, I can either take the average value in that 5 meter sample step, the shoalest value, or we can display a high-low line. So being that we're looking at a shoal here, I'm going to leave the shoalest value. I'm going to hit Apply. So you can see that that's now updated my graph. I can also export this to an ASCII or an image for use in other publications. So I'm going to dock that window back down here. And another handy feature is that once you've created these profiles, you can actually select the profiles on the profile layer, and it will show the profile for that line in the window. So the next thing that I'm going to show is the conformance analysis. So I'm going to go Tools, I'm going to highlight the depth layer, I'm going to go Tools, Conformance, Analyze Conformance. So this brings up my color range file. So you can choose to edit this if you'd like to change it around, but we'll just leave it as default, and I'm going to hit OK. Now my guess is 5 seconds for this.
4 seconds.
Ooh. Boom. Now what this has done is it's created a new CSAR file, and it's given it a color range file showing the difference between my shoal survey and my reference model. So once again, just highlighting the areas in green are safe areas where the bathymetry is over 1 meter deeper than the model. Yellow is the cautionary areas where we've got less than 1 meter of clearance. And as we go up here, we've got areas in red as our danger areas where we've got shoals. Now, another handy feature with this is, being a CSAR file, you can export it to a TIFF image, which I've already done. So I'm going to open up that TIFF image. And we can actually create a really good 3D view out of this. So I'm going to turn on my 3D viewer. I'll turn on my depth layer. And I'm going to drape an image over that. So if I drape my conformance view image over it, you can see now we've got our conformance view draped over our bathymetry. We can give that a bit of exaggeration. And once again, we can create a fly-through of our channel showing the safe areas and showing the cautionary areas and showing where we've got shoals. So we're running out of time here, but the last feature that I'm going to demonstrate for you, let me just get rid of a couple of these layers, is the shoal detection. So once again, I highlight the depth layer of my shoal survey, and I'm going to go Tools, Shoals, Detect Shoals. So here I can select my reference model, and here I can group my shoals. So the group areas is the horizontal proximity of the shoals. The split boxes at each 0.2 meters, that divides my shoals into 0.2 meter depths. Now once again, to sound like a cooking show, here's one I prepared earlier just to save some time. So if I open up my detected shoals, this is the result. So it creates shoal boxes around my shoals, and it also creates some contours for them. So if I highlight these shoal boxes and have a look at the attributes, you can see that I've got the minimum depth in my shoal box, whether the shoal has been registered in a database, and the status of the shoal. So as I look at these three boxes here, this one is at 12.1 metres, we've got this shoal at 11.9 and that one at 12.3. So that's showing the 0.2 metre intervals that the shoals were created at. So if we go back to this shoal down the bottom here, so I could highlight this shoal and I could go Tools, Shoals, I could register that in a database. That's just a Microsoft Access database, so once I've got that going I can import from that database, or I can change the status of the shoal to cancelled in the database, because as we saw before in the profile, that shoal has been cleared. Now, should that shoal be existing and we need to inform mariners, I've got the option. So if we zoom in, I get this in the display. I can go New Publication again. This time I'm going to use my default shoal publication, and all of the available information is there in the window, and I'm going to go Preview, and there you can see our shoal publication. So in our shoal publication we have the position of the shoal, the coordinates, we have the depth of the shoal, we have the maintained depth of the channel, length and width, and our clearances for the channel. Now once again, this can be customized so that you can have your own information here and your own logos. And look, that's pretty much brought me to the end of the engineering analysis demo. So I'm going to go back to the PowerPoint now. And just quickly, I thought we'd give you guys a bit of an overview of what we can see in the future of BDB. So some of the future enhancements that we're looking for is to apply a filter when connecting to the database. We'll also be looking at GDAL support for CSAR and BAG files. We'll also have some new BAG export options, such as a new dialog, export any elevation band, metadata template, the ability to break into tiles, and also support for designated soundings.
We also have extra processes added to the CARIS batch executable for interpolating surfaces and exporting to bags. We also have nested grids and variable resolution that's coming up. You can see that in the background right now. That's actually what we're going to do for that is if you have multiple kind of surfaces, what you can do is actually bring in and combine both of those surfaces without actually having to combine them to the coarser resolution of the two. So as you can see in this picture here with what seems to be some potholes, that where the surfaces connect, it'll see that connection, but you'll be able to retain the really fine resolution where you've actually collected it. We're actually going to be implementing 64-bit for server and client applications, so Base Editor, Base Manager, and Bathy DataBASE Server. And we'll also be able to create geospatial PDFs. So yeah, I guess I hope you guys enjoyed the webinar and that you will come to our next one.
And yeah, please feel free, as well as any questions, if you have any feedback or suggestions, please send them through to us.